Yes, first speaker, very pleased to have Luis Ibanez talking about SUSY breaking scale and F theory unification.
Okay. Thank you very much for your kind invitation. So this is work done in collaboration with Fernando Marchesano and our students Diego Regalas and Irene Valenzuela. Okay, we were very excited on December the 13th when this famous announcement of the first scene of the Higgs were found, with some Higgs seen at around 125 GeV, both in CMS and Atlas. Apparently, there are very convincing rumors that these signals are going to be confirmed next week. So, okay, so for now, I'm going to assume that there is indeed a Higgs around 125 GeV. Okay. It's working? So there are some casualties. Technicolor is in trouble. Of course, headless models, by definition, would be in trouble. But there is another important LHC input, that there is no new physics yet. Even, well, there are some important models which are already in trouble. This is the prediction of Homer-Simpson. Look at this. This is pi alpha electromagnetic to the 8th Planck scale. So this is what you can read here. So it's 303 GeV. So this also, not only Technicolor, but Homer's model is ruled out. So what about supersymmetry? Well, supersymmetry predicts that the mass of the lightest Higgs is lighter than 130 GeV. So in principle, 125 GeV Higgs is good news for supersymmetry. However, this value is a bit high, one must admit. Let us recall a few things about the mass of the lightest Higgs. In the MSSM, there is a three-level contribution, which is essentially given by the set mass. So for this further one is at most 90 GeV. And there is this loop correction, which should be quite big in order to reach 125 GeV. It is potentially big, in fact, because it goes like the fourth power of the top mass. There are also parameters involved, all of them related to the top system, because that's the one which is most relevant in the one-loop contribution to the Higgs mass. We define this stop mass as the geometric average of both masses of left and right stops. And this is the off-diagonal term in the mathematics of stops. And A is the A parameter. Well, there are certain ratios of xt, well, in particular when these ratios are 2.4, which enhance this quantity. But in any event, you need typically a squares quite heavy to reach such large values. And in fact, if you restrict to models with squarks lighter than 3 TeV or a bit more, 4 or 5 TeV, some models like the simplest setting of anomaly mediation, gauge mediation, noise scale models have difficulties in reaching such large values, although the constraint MSSM is still alive. But I said you have to fine-tune your parameters a bit. This plot is by Lawrence Hall and collaborators, and you have this SUSY breaking scale, the average mass of the stops, versus this off-diagonal term in the stop mass matrix, and this red and blue are lines consistent with 125 GeV Higgs, and these lines in here, these continuous ones, indicate the amount of fine-tuning you need to obtain supersymmetry breaking. This is in the MSSM, not in the constraint MSSM. So this is 1 per mil fine-tuning in here, 1 in 500. There are two branches, okay? So in general, you need substantial fine-tuning. There is an additional fine-tuning typically present also, because one of the triumphs of supersymmetry, which is the natural existence of neutralino Higgsino dark matter, is typically overabundant unless you have an additional fine-tuning also for further 1%, 1 per mil. Okay, so it is of course premature to give up on the SUSY solution to the ERK problem. In fact, I believe it is premature. So it's not, there is a lot of things which can go on. But imagine that after running LHC at 14 TeV at full luminosity for several years, there is no new physics at all. Not only no SUSY, but no physics. So maybe we will have to reconsider again the fine-tuning solution to the hierarchy problem. Yes, there is a fine-tuning there. And it's a possible anthropic origin. If the Higgs is not light enough, it cannot trigger electroweak symmetry breaking at the right scale and give rise to a sufficiently complex universe with sufficiently complex chemical elements so that we can exist and observe it. So that's the typical anthropic argumentation. So let us give up on low energy SUSY for a while to see what happens. Okay, we will see it in a few years if this is required or not. So the first simplest idea for people old enough like me is, well, let us go back to good old non-supersymmetric SU5. Why not? We don't have SUSY. But recall that there are some limitations for the minimal non-SUSY SU5. You have wrong gauge coupling unification. You have too fast proton decay because the unification scale is a bit low. This in the minimal versions of SU5. Wrong first generation masses, again in the simplest version of SU5. There is perhaps another hint against just assuming that there is a non-SUSY desert up to the unification scale, which is the following. Now, if the Higgs is there, we know what is lambda, the self-coupling of the Higgs at the electroweak scale is given by this expression. Is the mass of the Higgs that we know, the mass of the W that we know, G2. So we know lambda at the electroweak scale. Then we can run down in energies, although everybody thinks that the lambda 5 to the 4 is something which is non-asymptotically free due to the top loop correction, which is very strong. In fact, lambda is asymptotically free. I mean, it goes down in energies. This is the renormalization scale. This is the value of lambda. And it seems to vanish at around a scale of 10 to the 10, 10 to 11 GeV. That depends on the precise value of the Higgs mass for 124. And it's sensitive to the top mass. There are more recent calculations by Strumi and collaborators in which these errors are reduced. And again, typically, lambda is vanishing at around 10 to 11 GeV, apparently. That may mean something. It's not necessarily, it's not a disaster for the standard model in the sense that it is true that the scalar potential of the standard model becomes unstable, but well, we could be living in a metastable vacuum and nothing is wrong. Okay, but I don't know. It may be indicating that there is something happening at around this intermediate scale 10 to the 11. There could be some new theory regulating this vanishing value of lambda so that it cannot become negative. Okay. Anyway, our philosophy is that even if SUSY is not present at low energies at the electroweak scale, string theory suggests that it's present at some scale, MSS, below the string scale but above the electroweak scale, to get rid of, to be sure that we don't have tachyons. Typically, even non-supersymmetric models have scalars, and it's very easy to get tachyons in a theory which is non-supersymmetric. So, seems a reasonable option to have supersymmetry at some scale, not necessarily the electroweak scale, but larger. One thing we want to keep is gauge coupling unification, and we've been listening to very interesting talks in this conference about the promising framework, which is F-theory grand unified theories. The reason why people like F-theory grand unification is because it is consistent with the type 2b F-theory modular fixing roadmap, which explicitly exists in terms of fluxes, closed-in fluxes, and perhaps non-perturbative effects, etc. There is a way in which we know that moduli could be fixed. And secondly, this is an advantage compared to perturbative type 2b. One can get a large top quark mass. Okay, so we consider F-theory SU5 unification, or I mean, many of the things I'm going to say really are perturbative type 2b statements, but not all of them, as we will see later, without any prejudice about what the supersymmetry breaking scale MSS, I will call MSS, is. And of course, as I said, we want to obtain at least correct gauge coupling unification consistency with 125 GeV Higgs, and being having a proton sufficiently stable. Okay, so this is a course on F-theory in 3 minutes, because you know everything. You have heard this kind of thing several times this conference. So So what's F theory SU5? Well, F theory may be considered, as you know, as a non-perturbative extension of type 2B orientifolds. One considers, if you're interested in four-dimensional theories, a 12-dimensional theory on a complex fourfold, such that it is locally, well, it's an elliptic fibration. So locally it's a 2 torus times 3 complex manifold, and you identify this 2 torus with, I mean, the complex structure you identify with the complex dilaton of type 2B. There is this general idea that you have a 6-dimensional manifold with 3, and then the physics, the SU5 physics, is related to a 4-cycle S, which contains the SU5 degrees of freedom, and the matter fields, I mean the 10s and the 5-plus and the Higgs, belong to so-called matter curves. And this is the way it arises. You have the SU5 degrees of freedom in S, and there are intuitively some intersections with extra U1s corresponding to other 7 branes, and at the intersection curves there is an enhanced symmetry, and then you have localized matter fields, in this case in the template, in this case in the 5 bars. In addition, to get chirality, you need some fluxes along these U1s in your theory, and to break SU5 down to the standard model, one assumes that there is some hypercharged flux. Finally, Yukawa couplings appear when 3 of these matter curves, which contain left and right handed fermions, intersect the Higgs branch. And in principle, they depend on local properties, and you can compute them in terms of overlap integrals, like Fernando Machesano was explaining us yesterday. So that's the end of the course on F theory. So let us consider the mass scales in this setting, which I will use perturbative equations in here. So there are essentially 3 relevant scales. One is the string scale, which is related to the alpha prime in the usual way, in this way. The Planck scale, which is related to the string scale, but mostly to the volume of the B3 compact manifold. And then there is the compactification of unification scale. Let us recall it that in this setting, 1 over alpha g, where alpha g is the unification SU5 unified scale, is related to the volume of the fourfold S by this expression. So if we parameterize this volume in terms of this RC, 2 pi RC to the 4th, then we define unification scale as 1 over RC. And then, okay, plug in this expression, you get this relationship between the compactification scale and the string scale. Putting here numbers, alpha g for the 1 over 24, 1 over 30, whatever it's your model, and yes, that we will see are smaller than 1 typically in the cases we will consider. This is something which is slightly below 1, so it's 0.5 or 0.4. So the compactification scale is slightly below the string scale. Okay, so as I said, SU5 symmetry breaking is achieved in this setting by assuming there is a flux along the hypercharge direction, and these fluxes are quantized in any 2 cycle in S. Okay, so on dimensional grounds, you see that the value of these fluxes are 1 over of order 1 over RC squared, so that this is of order an integer. So that means that the fluxes of hypercharge fluxes are of order of this unification scale 2 squared. So really MC is the unification scale, in the sense is that that's the scale in which SU5 is broken to the standard model. Okay, another interesting ingredient that we will going to take into account is the generic presence of closed string fluxes. It's something generic. It's not that I'm adding it. In any compactification, typically you will have closed string fluxes, and they are a natural source of SUSY breaking. So we all know that in type 2B there are Ramon and Neves-Bar 3-form fluxes, G3, which induce generically SUSY breaking soft terms, unless they are of some precise type or are diluted. Typically they break SUSY, and the soft terms whose scale I define to be MSS is of order of these fluxes. And since these fluxes are quantized on 3 cycles in the large bulk, okay, so their size is of order alpha prime divided by the square root of the volume. So this goes like 1 over r cubed, if you wish. So, and that corresponds to string scale squared divided by Planck scale. And writing here the string scale in terms of the unification scale MC, you find this expression for the supersymmetry breaking scale. This something which again is something of order 1, goes like compactification unification scale squared divided by Planck scale. Okay. So this is what you expect if you don't ask anything special about the fluxes, that they have their natural value. Know that this is not what you do in when you do compactifications in which you wish to obtain the MSSM scenario. You need to dilute these fluxes somehow, because otherwise this would be too large. This is not going to be a weak scale, they are going to be too large. So the tacit assumption in any analysis is that these fluxes are suppressed by some reason, some warping factor. For some reason the fluxes are diluted in the area in which your brains are sitting. So that's the tacit assumption. Here we just allow it for the fluxes to get the most general value. Okay, so let's go now to gauge coupling unification. To lead in order, in an SU5 setting, the 3 gauge coupling functions are related to the same field, which is the local color modulus in the 4 cycle S, which we call T. This is the complex color modulus. But as pointed out by some people in the audience, in some other people, there are corrections coming from when you have extra fluxes, like in particular I will concentrate it in hypercharged fluxes. There are corrections in particular to the SU2 and the U1 gauge kinetic functions, which are linear in the complex dilaton tau. Tau is the complex, this real part is 1 over GS. GS is the Ti 2b dilaton. Okay, and these fluxes are assumed to obey some condition to avoid exotics, as we already heard these days. Okay, so these corrections are in principle important if you just give reasonable numbers to the quantities in here. In fact, they may be problematic even for the MSSM. Okay, so what they do is that instead of having the usual SU5 unification prediction, which is this, you have this generalization. There is a relationship between the 3 inverse coupling constants. One can see that the size of the corrections are controlled by the string dilator 1 over GS. Okay, so if you are at weak coupling, this threshold correction is large. On the opposite side, if you are in the MSSM and you want these threshold corrections to be small, you need GS big. GS big, still notice that we are in F theory. GS is not necessarily small. Also, it's not something which is well defined. So we are thinking here of GS as a sort of average in the region in which your brains are. Okay, so let me assume that there are two regions. The energies in between the electron width scale and the SUSY breaking scale, in which you have the standard model. You have the standard model, and then there is above MSS, you have the MSSM or some simple extension, like having extra doublets or triplets. I mean, you don't need to have precisely the content of the MSSM. This is similar to the so-called high-scale SUSY breaking scenario of Hall and Nomura, in fact. Okay, so just using the renormalization group equations, this is a one-loop analysis where you just put the beta functions for the non-SUSY sector and the SUSY sector, and you just put in the central values of the coupling constants. What you get, as you can see from here, is just a line in the in the plane log MC log MSS. I recall you that MC is the unification scale, MSS is the supersymmetry breaking scale. So this is the unification scale MC. This is the SUSY breaking scale MSS, and this is the line I'm talking about. So in this line, you get one loop gauge coupling unification. Okay. As you go in this line, the value of GS varies. In this region, you are well, in essentially all this region, GS is smaller than 1. Whereas in here, when MSS is small, it's close to 1 TeV. You are in the MSSM region, so GS you need a GSS for the 6, 7, something like that. Okay, on the other hand, this line here is just these relations I showed you before between the SUSY breaking scale and the unification scale MC. This is this line. So they cross at a scale of order 10 to the close to 10 to the 11 GeV, particularly 5, 10 to the 10 GeV. And in this, if MSS has that value, then you get consistency both with gauge coupling unification and genetic SUSY breaking induced by genetic fluxes. So, and the unification scale is relatively low, 310 to the 14 GeV. Okay, so so the structure of the theory is this: you have the standard model below MSS. Okay, you have lambda, which I will discuss in a minute, which goes and vanishes close to MSS. And okay, then you have this region with MSSM of some generalization, and which don't quite unify because you have these threshold corrections I told you about, which are well defined and computable. An important point to remark is that these curves are independent of the presence of not of additional triplets or doublets above MSS. So you could have additional triplets, you get the same curves. That's because those fields do not contribute to this quantity, which is the combination which is relevant for this running here. So this is interesting because in fact, in this setting, you don't need the famous doublet-triplet splitting. If SUSY breaking scale MSS is 10 to 11 GeV or so, then the Higgs triplets get a mass of 10 to 11 GeV, assuming typical couplings for the first generation, which are highly suppressed. Then you get proton decay, under control. So you don't really need to do doublet-triplet splitting. You may do it if you like it, but you don't really need it. So that could be an advantage. As I said, the dilaton varies depending on what MSS is. In our region, it's 0.47. If you have these extra triplets, which may be light, you also get GS strong. It's different dependence, but okay. So let us go back with this. We already said that at 10 to the 11 GeV or so, lambda seems to vanish. So perhaps it's not a coincidence. So what could be the justification of that in this setting? Why lambda is for this 0 is vanishes close to this intermediate scale? Well, it turns out to be natural within large classes of string compactifications. Above MSS, or the SUSY breaking scale, we know we have two doublets, HUHD, and below we have just a linear combination with some angle beta. Okay, so then there is a standard model quartic potential inherited from the MSSM diter, which is given by this expression. So this is the lambda that you expect in the scheme. So the fact that it vanishes at this scale means that tangent beta is of order 1 at that scale. So why that should be the case? Well, it's sort of reasonable in these string settings. This is the most general mass matrix for the Higgs HUHD. With off-diagonal terms and diagonal terms. As I said, there is a massless eigenstate. Now, this massless eigenstate is obtained whenever this is fulfilled. This is the condition to get a massless boson. Of course, I am assuming here all the Lucas ratios you can imagine. So this is so the defined tuner really guarantees with sufficient precision, anthropically tuned, that there is a massless doublet. Anyway, once this is fulfilled, the tangent beta is just the ratio of these two masses here. Okay, so to get tangent beta of order 1 at that scale, what one needs is that these two diagonal masses are approximately equal. But this is sort of quite generic in stick compactifications. In particular, that happens whenever your Higgs appear in some n equals to hypermultiplex sector in some limit. Also, of course, if there is a mu term, that's also give you terms which are symmetric. So, for example, in this intersecting or the magnetized version of this toroidal standard model type 2B orientifos, you have diagonal masses from in terms of the distance between the branes of SU2 and U1, which give rise to the Higgses, and there are off-diagonal contributions to the masses from the misalignment of the fluxes. Okay, this type of off-diagonal terms do appear also in F theory. You have your Higgses in some Higgs matter curve, and you have no fluxes there, but then you have a 6-dimensional equals 1 hypermultiple structure, so you have n equals 2 hypermultiple in 4 dimensions. And then locally you have some fluxes, and J is the local color form. Then the determined condition is phi f wash G is equal to 0. So whenever you have if this is not 0, you get an off-diagonal term and 3 halves. So In principle, you can fine-tune the existence of a massless Higgs by fine-tuning your fluxes, or your flux densities, in fact. Also, this is one way to get all these terms, but there is another generic way. This is from closing fluxes, the same closing fluxes I showed you before. We all know that they induce, one way to describe these fluxes is giving non-vanishing auxiliary fields for the color moduli of the compactification, in particular to the local color modulus T. This has been recently emphasized by Hebecker, Nogel, and Weigand. And okay, if you have n equals to hypermultiple structure, your color metric takes this form, I mean, multiplied by some moduli dependent factor, but the crucial point is this structure. Then immediately you can see that assuming that the auxiliary fields of the moduli get BEVs, you get a structure for the potential of this form. So indeed, the masses of your Higgs diagonal masses are equal. And in fact, in this case, m equals to the 3 level, this is an identity. So you get 3 level tangent beta equals to 1. Well, I will not get much into it. This is, of course, in the region in between MSS and MC. This gets renormalized. It's something you can compute using the standard one-loop renormalization group equations of the MSSM. And there is very little dependence. So tangent beta goes instead of 1 to 1.2 to 1.4, depending on the value of the top quark in this region of interest. So it's okay. So this is our situation here. So these two curves meet at this 10 to the 11 point, but there is now, in some way, the nice property that the Higgs mass observed, if it's there 125 GeV, is consistent with an intermediate MSS scale. So three nice pieces of evidence coincide. There is a question of proton stability because the value of our XY massive gauge bosons of SU5 is low, 10 to the 14 GeV, and the superconductor limits for SU5 tell you that this gauge boson should be more massive than 10 to the 15 GeV, or so there is a sort of a factor of 5 to light to obey the superconductor limits. However, it's important to realize that in the case of F-theory compactifications, the couplings of gauge bosons to matter fields are not just G. They change because of the localization effect of the fluxes. This is the way you compute a coupling of a massive gauge boson to a couple of templates or 5-plets in F-theory SU5. And then, well, you can, I cannot give the details, consider these local wave functions like the ones that Fernando Marchesano was discussing, where, well, this is an expansion around x equal to 0, y equals to 0. Well, in this case, the matter curve is localized at y equals to 0. This is due to this exponential here. When you add fluxes m corresponding to the ones that give rise to chirality, and hypercharged fluxes, which are hidden in this QS here, you get this form of wave function. On the other hand, the massive xy gets localized in the presence of hypercharged fluxes in this way. So in principle, you can do these integrations, and then, great. In the absence of hypercharged fluxes, that gives you what you expect, something proportional to G. On the other hand, in the presence of hypercharged fluxes, what happens is that instead of being the gauge bosons living in the complete S, they get localized in some Gaussian. So the overlap integral becomes smaller. Setting this wave function in the same wave function matter curve as the matter fields, you can compute them explicitly. I just go in a simplified expression. There is a bigger expression, but for fluxes smaller than the string F-theory scale, this is a factor of suppression that you get. So if these fluxes are of the similar order, this and this is 1/2, say. This is y is the generation number. So for the first generation, you get 1/2 to the 3, so you get a suppression of order 1/8. But this is a pessimist interpretation, because if the wave function of your xy's are away from the matter curve, which is something more generic, you expect, in fact, a more dramatic suppression. So this is completely different from the Higgs effect, in which the coupling of the massive gauge bosons to the fermions is the same before and after SUSY breaking. Okay, so we could be perhaps close to the limits of proton decay. So classical proton decay of non-SUSY SU5 going to this leading mode could appear. Although, of course, I told you, if there are these triplets which survive at the intermediate scale, there could be also proton decay modes of this form. Okay, cover the last topic before the conclusions, which is possible actions. The strong CP problem has no obvious anthropic solution to my mind. On the other hand, we are happy that string theory in principle has natural action candidates. For example, recall that the gauge kinetic function of SU3 is proportional to this. In particular, the imaginary part of T could be an action candidate. Here there is also the imaginary part of tau, but that's that's generically fixed when you in the presence of fluxes. So one can compute the action decay coupling constant in this setting in terms of just the form of the color potential, the kinetic term of this T field. That's quite independent of the form of the color potential, but assuming in particular in this case the computation has to be done using this Swiss cheese structure considered by Fernando and collaborators, you find that the axionic decay constant is some number of order 1 times mc over 16 pi square. Which is okay, since mc is of order 10 to the 14, you get an action decay constant 10 to the 12 GeV, which is interesting because precisely that's the region in which that could be an interesting candidate for dark matter. Let me state that it's non-trivial that this imaginary T field survives all the dynamics which fixes the moduli. So there are ways in which the imaginary part of T can be protected from moduli fixing effects or other effects which can give. So that's of course something which has to be proved, whether this imaginary part of T can survive after moduli fixing. Okay, so let me just mention that in this setting one gets an axion mass of order 2.7 10 to the minus 6 electron volts, and the ratio of the decay amplitude over the mass is of order 1.4 10 to the minus 16. And note these limits of ADMX, which are microwave cavity experiments searching for cosmic actions, are in fact quite close. This rho is the local dark matter density. Okay, so and the future improvements could test an action in this area. Perfect timing. So let me just conclude. If after the 14 TeV run no sign of SUSY is seen, a substantial fine-tuning of parameters will be required for the 1 per mil probably. So and I mean, imagine the worst scenario. It's not the scenario I would like to have, but imagine that's the case and there is no SUSY. There, the case makes sense to consider, as I said, fine-tuning back in business. I insist that string theory in some way suggests the presence of unbroken supersymmetry at some scale, not necessarily at the electron width scale, and we have presented several arguments for a supersymmetry breaking scale at this intermediate scale, with a unification scale somewhat relatively low compared to the normal unification scale 10 to the 13. But there are several arguments in favor of this structure: gauge coupling unification from threshold corrections, flux-induced SUSY breaking, consistency with the Higgs mass around 135 GeV, and this action with the principal biaxial decay constant. And as I said, although the unification scale is low, the proton is sufficiently stable due to a novel effect in F-theory involving wave function localization. This condition, that tangent beta around the SUSY breaking scales of order 1, which is the same as this, arises naturally in string compactification with the Higgs sector with an underlying equals to structure, which is then later broken by fluxes, so it gives you this M3 of the diagonal term. Let me tell you that there is no need for double triple splitting nor R parity symmetries in here. I mean, R parity is again not required for any reason if the mass of the quark is left to 10 to 11 GeV. Dimension 4 operators are not dangerous. I mean, they can again give rise to dimension 6 proton decay operators, but you are in the verse. You are in the region in which they are not a phenomenological disaster. So of course, for model builders, this is paradise. Imagine your F-theory model. You don't need to do double triple splitting. You don't need to look for R parity. This is a nightmare. This is why you need to introduce the U1 Peccei Queen F-theory model, whatever. So it would be good, of course. Well, there is something which can go wrong soon. If there is increased precision in both the Higgs mass and the top quark mass, then we will really check if really lambda is vanishing at 10 to the 11 GeV or not, because it's still not ruled out. I mean, if the errors in the top quark is large, it could be that it vanishes close to the Planck scale, like some German authors claim. Unfortunately, there is no new physics at LHC, so it's the pity of this. And well, action detection and proton decay could provide information on this scheme, although will not be necessarily a smoking gun for it. Okay, so that's it. Thank you. Let me remind you that there is a very interesting workshop, new challenges for SIM phenomenology, will take place at the end of September in the glorious new building of IST in Madrid. You are all invited.
So thank you very much for that very nice talk. There's loads of questions. So Stuart, start to the front.
Yeah, so it's a simple question. Why do you say there's no doublet triplet splitting? The triplets have to be big, around 10 to the 14 GeV here? Or 10 to the
10, I mean, the actual limits are 10 to the 11, not 10 to the 14.
Higgs doublets are at the weak scale.
Sorry?
I don't understand. Isn't that a splitting? The triplets are at 10 to the 10 or whatever? No?
No, I'm saying that if they have a mass 10 to 11,
Yes.
that's good enough. That's the limit.
But that's still, but the Higgs doublets are at the weak scale.
No, they haven't. No. It's in MSS. I mean, the scale of supersymmetry breaking, you have both doublets and triplets, and then below only you only have doublets.
Isn't that splitting?
Oh yes, because if you fine no, it's not. It's a splitting, but it's natural in the sense that if you fine tune a massless doublet, if you fine tune a massless doublet, generically you will not fine tune a massless triplet. That's it's much more costly. You don't need. This is an anthropic. If you wish, it's an anthropic doublet triplet split.
Okay.
Anthropic selects massless Higgs. It's not interested in having a massless triplet.
But isn't that just another name for fine tuning?
Oh yes, this is pure fine tuning. So we would admit that we were lost for 25 years with this fine tuning. No, but I mean, once you fine tune the Higgs, then you don't need to fine tune the triplet. Yes.
So how much improvement top quark mass and Higgs boson mass improvement you would need to have better prospect for this lambda at infinite scale vanishing?
Well,
for the top quark mass, you already have.
I mean, there is this. In fact, these plots I showed to you have been improved by a Strumian collaborator recently, and I would say that there is. Vanishing of lambda at higher scales, 10 to the 18 GeV or 10 to 19, is already 2 sigma away. So it's already 2 sigma away. So I mean, maybe there could be some surprise with the LHC experiments. We will get precision for the top quark mass better than CDF soon. So I don't know. I think it's unlikely that this changes. So it seems that lambda is vanishing at the intermediate scale or so. Yeah.
I have a conceptual question. You showed throughout your talk these kind of expressions where you have this correction due to the fluxes, and there's always this tau appearing in front, so that it's that is a recoupling expression, right?
Yeah.
So how do you know that you can use this for such an F-theory gut, and that any of these conclusions are still valid?
As I told you, this essentially all but the discussion of the suppression of the proton decay operator can be done in intertubate cycle B. I mean, it's a. F theory, as you know well, in fact, you haven't reproduced precisely this.
But I just reproduced these at recoupling. Yeah, there are a lot of corrections once you go away from recoupling, so you don't know if these could spoil.
I think this is the best we can do at the moment. If you can do better, it's.
Right. Self-consistency, you are at recoupling.
Yeah, I am at recoupling.
So it's self-consistent.
Yeah.
But I thought it's an F-theory gut, no?
Yeah.
Well, that F-theory doesn't mean with coupling. I mean,
Even if you
it means
ignore
that the coupling is not globally defined. It's a different thing.
Comment now. Even if you ignore that, these issues with recoupling, Donagi-Weinhold actually pointed out that there are very important high-scale threshold corrections And also, did you include, say, higher loop corrections and no scale threshold corrections in your analysis of the unification?
Yes.
Did you?
Well, I don't know if they are large or small,
They
the
are
threshold
large.
corrections.
We actually computed.
That you mean Kaluza-Klein, ball, etc. I'm sure that depends on the choice of parameters and how far away you put your.
I mean, those are very important
You
corrections.
can yes.
And in fact, when you don't include them, a lot of things change. You know, it's the high scale threshold corrections. I pointed out yesterday. It's they depend on the specific model.
Yeah.
But in a model, when they're actually computed, they give a really huge correction, and they actually do not, like the two-loop correction, satisfy the Bloom-Hung relation.
Mhm.
So in fact, you know, they're extra, and they make the whole picture a little bit more subtle. So I think they're very important, and I think you have to take them into account. Just to
This is also a one-loop computation. So
Yes, so
the
you have
two
to do
loops,
two
the two
loops
loops.
also.
Anyway, here these corrections are they are large, for the 9% or something like that to the couplet. So.
So,
And two-loop corrections are not that big.
no, actually we checked in, you know, a very large class of, you know, you just said some SUSY. Two-loop corrections had a big effect, in particular because of all these other things from the hypercharged flux, etc. So
But you mean at the large scale? Okay, I was talking about the running. at
even
the
the
local
running,
scale.
yes. Also, the two-loop corrections are important, and they spoil the Bloom-Hung relation. So it's, you know,
We'd like to see that.
you really have to include it.
When considering the n equal 2 sector for the Higgs, how do you envisage getting the mu term? At the beginning you said, so in intersecting brands you could get the mu term, so to speak, by just tuning the terms. What do you have in mind in this case when the Higgs is localized on a curve?
You mean having at the same time the n equals 2 structure and a mu term? You mean? Well, it's like in these toroidal models, it's not actually a mu term, it's really a couplet of a singlet. It's more like an MSSM. So it's a coupling of a singlet to HS bar. That's present in many of these models, in fact, like in the simplest models. So it's more than a mu term. It's really a coupling of a singlet times HUHT. And this singlet is really the distance between two branes, and that's perfectly consistent with an n equals 2 structure. So.
Yeah, but this you don't have anymore. If you have everything on on a curve, on a 5 curve, you want to.
That thing, for example, like in F theory curve, you don't have such thing.
Yes.
Correct.
So what?
So it's no. I was showing a list of possible contributions. So it is really, on the other hand, the fluxes or SUSY breaking from the auxiliary field of the TIF is really really needed in F theory to get that result. I mean, it's not indeed that mu term is not obvious how it could come in the F theory context. You're right.
But if
I was just putting a list of possible contributions.
If I accept your Keller potentials, HU dagger plus HU squares, then I think you have Giudice Masciero, right? To the mu.
Yes, in that example there is Giudice Masciero.
Yeah.
So what? Giudice Masciero is yeah.
That can
Typically-
that can give the correct mu term, right?
Yes. In fact, as these people pointed out, due to the Giudice Masciero type of structure built in, you get tangent beta equals to 1 to lead the order.
Yeah, we'll take just one more. Right? You have
Yeah,
a
so
go.
first,
So to expand.
You already asked.
I mean, to some extent, if we have a high-scale SUSY, the general opinion seems to be that we give up on solving the little hierarchy problem. But is it possible to quantify how much fine-tuning we are doing when we have such an intermediate scale SUSY breaking, in the sense of, is there something like Giudice
No,
boundary
it's,
that you can
You can imagine it's 10 to 11, it's 10 to 8, 10 to the 16, one in 10
well,
to
no,
the
it's
16.
some intermediate scale. I mean,
It's a sizable fine-tuning. Yeah.
but would you say it's 10 to the 8?
Compared to 1 to the 1 over 1,000, which is you will get.
But you would say it's fine-tuning of, say, 10 to the 8, 10 to the 11.
I would say 10 to the 8, but these are mass parameters squared, so I would say 10 to the 16.
Okay, so we should probably move on. Sorry. So thank you very much again.
Okay.